them out, and you can again screen both of the compounds against your receptor value. Simultaneously, you can dock different fragments, different sections of your compounds, and maybe you can come up with a new lead. Like here, whatever the earlier spacing was there, this can be changed to this kind of spacing. So a new compound you came up by reassembling the fragments. So this is the purpose of your this molecular docking, that you can come up with so many different compounds which can show you the good amount of strength, and that can be considered as the best possible compound. Now, if you want to see these things in more detail, first what you need to understand, you should now talk actually about a pharmaceutical drug. What is exactly a pharmaceutical drug? Can anyone define what a pharmaceutical drug actually do? If you want to understand molecular docking, first you should understand what exactly a drug molecule do. Binds with the receptor in the body. Okay, this is what something you have understood till now, whatever I explained to you. So if you want to go into more detail, so I can define it like this. Pharmaceutical drug molecule is a small molecule, always it's a small molecule, that is going to bind to the receptor. This you have understood till now, because in the ADME and initially also while giving the introduction to drug discovery, I said that there are some pockets and there the compound has to bind. But there are other things that you should consider. These terminologies which we haven't used in the our earlier method, which was QSR. Here the this term is very important. That is, last time also I told you, the word interaction. The interaction of one molecule with some other molecule is important, and that we have to now we should be able to calculate it at the level of the computer. Once the binding happens, this will happen only after the two things are coming closer, and if they are having some kind of, they can have some kind of repulsion also, the two compound, but the repulsion, if it is there, it is not going to bind, so that particular component is no longer useful to you. But still, even though it is repulsion, or if even if it is attraction, you want to know that interaction in terms of some value. So that is what we are focusing in this particular method. Once this interaction and binding happens, then you know that somehow after the binding it is going to control the function of the biological receptor. How can it control the function of the biological receptor? I had given you till now so many different examples, like how the controlling of some function can happen, like because of which some disease can be cured. Can anyone give me the example how the control of the function can occur? Guys, be a little bit interactive. Okay, I will show you some video. Just a minute. Okay, I hope you can see this video. Okay, now I said there are two stuff, and both of them are going to bind to each other, and they are going to bind means they are going to interact also. So how this thing happens, I'm going to show you one video, like you can consider some sophisticated calculation people can do using even more complicated way. So this is the video from those particular method. So here you can see this, something is happening. Can you focus exactly what is going on here? Okay, I'm showing the video again. Just anyone explains to me what is exactly happening. Can someone comment on this? What is going on here?
Is going to interact with the receptor.
Okay, so you can see this video. Either I can slow it down, but I some pharmaceutical drug. Now it has somehow came close to a receptor molecule. Now what we are talking about, it came close, and now you can see this receptor. This is something like something a living stuff you can consider that is exactly happening, and this is you may be able to do this on the computer, that something is coming in the contact with some other molecule, and it is the receptor molecule, which is a very big molecule actually, and your pharmaceutical compound is like this, a very small compound, but it is coming in closer to the compound, and once it comes closer to the compound, you can see it is interacting with it, and it is binding also. So when I'm saying interacting, what can I say exactly? What do I mean by interacting? So interacting means two different components, how they are like, how they are behaving with each other. So here you can see some kind of white color lines are coming into picture. So these are some kind of interactions that is being taking place between the two different compound. And this is not just some kind of like two things are coming closer to each other, but one molecule, it is actually influencing the structure of the another molecule. Like you can see, generally if you see these kind of structures in reality, you can say that okay, they are even though they are flexible, these kind of structures like protein are flexible, but they are not easily alterable. You cannot easily alter their structure, but when something comes close to it, so it is making that structure to do all the kind of changes. This kind of changes, if you see at the bottom, it is they are calling it as some kind of conformational changes. What is the meaning of conformation? Conformation means structure. There are some structural changes that are being induced by the pharmaceutical compound that is coming in contact, and this is what happens. So in reality, if you want to understand this, I have given you so many times example. Just close this video, but just know this, that all these white color lines are some kind of interactions. Can anybody give me some example of interactions with respect to some names? What kind of interactions might be there?
Hydrogen bonding.
Hydrogen bonding, very good. Any other thing? Any other kind of interactions that can happen?
Electrostatic interactions.
Electrostatic interactions. Okay, any other? Okay, so all these things also we will slowly try to understand, but just know like this is a very good video for showing what exactly happens, that you can actually visualize inside the body. So now I said this is what happens when the pharmaceutical drug you are using, and this is what we are doing in the process of drug designing. We are coming up with a molecule which can favorably interact with the receptor, interact and bind to a biological target, so that whatever is our desired effect, like suppose if you want to remove the, suppose we are having some pain or some fever is there, so what we'll do, we'll take a paracetamol, and the paracetamol go within the body, but what it will do, there will be some receptors in your body called as some cannabinoid receptors there. This kind of components will go and bind to it, and they will be somewhat, they will be converted to some inactivated state. So these particular receptor, cannabinoid receptors, they will be responsible the sensation of pain and other things. So temporarily, even though that pain might be actually there, but you won't feel that, because this thing which is actually telling you something about the pain, that has been deactivated. So this is what you are always coming up for all the different types of diseases. What all these drugs are creating, the therapeutic means related to some like healing effect it is going to create. So here one thing is important to understand. Now we are talking about interaction. If you compare now two methods, earlier we had QSAR, now we are having the molecular docking method. So in QSAR, you had your pharmaceutical compounds, using which what did you estimated the descriptors values, and using this you estimated your criteria for screening activity value. Now in the molecular docking, what we are doing, we are having a receptor, something is binding to it, and we are coming up, we are trying to calculate some criteria, screening criteria, which will be related to our strength. So what is the difference in the two methods? Main difference you can see. for screening? Which is more realistic? Okay, docking is the more realistic method. Okay, why is it so? Docking, as we have the structure of the target. Okay, that is one of the aspect. So here I'm focusing on this word again and again. Why? Because in QSAR we had the structure of the molecule, but it was just like I always use the term like it was like a dead body. Means it, if you see it in reality, suppose there is some human being, but it's not alive. So just from that dead body also you can estimate some parameters. Okay, like you are able to measure the suppose height of that particular body, you are able to measure that. So this is what, like height you can consider as one of the descriptor more that you have estimated, and from that you are trying to talk about the activity value. So this you can consider, this is not like the something which is in reality you are making so much assumptions. Okay, but still it you can reach by utilizing so many of the descriptors. Like I said, hydrophobic city is one of the important factors. So if you are able to estimate the hydrophobicity value just from the structure of the molecule, so somewhat you can come closer to the value of the activity, but still there will be some assumptions that are coming into picture. Now, when you are talking about molecular docking, then what is the difference? Then you are actually making the molecules alive. Earlier, you had the dead molecules you can consider just simply from the structure you are able to talking. If two molecules are coming closer to each other, which you are not actually doing, but they don't know how to interact with each other. Both of them are dead. You don't know how one molecule is going to behave with the another molecule. But in docking, you are putting some kind of, this is again, or we are using some kind of computational method. But in this particular method, whatever the mathematical equations we are having, here also we had the mathematical equations, but here also we will have, but in these mathematical equations, there will be some criteria that will actually take into consideration how the two things should interact with each other. This is what I'm saying. The two things are being made actually alive, and then only you are coming up with the strength of the interaction. So based on this, you can consider that compared to earlier method, this is somewhat a more sophisticated method where we are actually putting soul within the dead bodies and then we are asking them to interact with each other. So this is what I said to you. We will do. We will have the biological target. We are going to have the ligand, and we are going to do docking. Docking means some kind of fitting. So you are having the target, and you are going to identify some ligand molecule which can fit within this target properly, and it should create that complex. So as even though in the cartoon representation it looks very good, but in reality this won't be that perfect. You can see some kind of gaps and other things also when two things are binding to each other, but that's what we are going to do. We are trying to identify the compound which can have the binding with the best possible way. So when you are talking about this docking, some concepts needs to be understood. One important concept is about molecular recognition. Now, from the word, you can consider the thing, two molecules should recognize each other. Now, if two things are there, they can have maybe this compound and this compound, both of them can fit very well compared to these two compounds because the both of them, there is a complementary shape and also size. So both the things can fit well each other. But there should be some other factors that is also important. If the two things are not able to recognize each other properly, then there is no use of just having the complementary shape. So both the things should be having some affinity towards each other. So molecular recognition is something, maybe this particular compound might not be able to recognize this particular compound because chemically this just not the structural way but also in the way of some chemical way, the two things should be having some affinity. So if they are not, they cannot bind. In the other case, sometimes you might have a compound which might not be that good in shape, but still it can bind because of the having the affinity. But still there should be at least some complementarity in terms of some shape. So this recognition, molecular recognition, it is important in all the like I said, QSAR is something a generalized method that you can utilize even for material design or something. Docking, most of the time people use it mainly for the drug design, although there are some other applications, but docking is a something sophisticated method for the identification of drug in the biological world. So many biological events are there in your body. If you know the biology in detail, there are transcription, translational, signal transduction, so many enzymatic catalysis kind of thing. And even if you see know about your COVID infection, how it happens and other things. So you can see so many times this kind of molecular recognition happens. Like two molecules needs to understand each other properly, otherwise the next stuff it is not done. If so this you can consider. So there is another term that is called as molecular modeling. What is this molecular modeling? Means just right now consider that we are going to put soul into the molecules. So molecular docking is just, you can consider one part of this. This later on molecular modeling in detail we will understand. But just right now you know that in the concept of molecular docking we are incorporating some kind of molecular modeling. Okay. So this there are different examples in your body how the binding and other things takes place. You can see. So when you know all this concept like molecular recognition, what is the use of this? The use of this is for controlling. But if you know anything, if you know the driving forces for any process, any physical or chemical process, so you can control that process or you can tune that process. Like for example, in your chemical engineering, also in your major subjects like mass transfer, heat transfer, momentum transfer, you always have some driving forces. Can anyone give me some example in mass transfer, momentum transfer, heat transfer? What kind of driving forces you are having? Okay, so concentration difference, we can consider mass transfer, temperature difference in heat transfer. Again, like if you consider momentum transfer, so velocity difference. So in all these processes, they takes place because of what? Because of some kind of differences are there. Some kind of there is a force. Something is less, something is more, and that's how that difference is important, which actually make that thing happen. So in this case also there is something. This molecular recognition is important, where actually if you understand the molecular recognition thing in detail, so you know something about the driving forces. When you know something about the driving forces means what? You know that what actually is controlling this binding. So most of the time you can consider some kind of affinity between the different groups is there, and this you can consider, as you have given the example, hydrogen bonding is there, or electrostatic interactions are there, or van der Waals interactions are there. So this thing you will know in detail, and using this interaction you can have some, like in the other case you have delta T, delta C, delta V. So in the same case you can have certain thing which can control the that process of binding, which we can consider by the function called as delta G. In other process also delta G should come into picture. Without that, if delta G is not negative, so none of the process will happen. So in this particular processes, we focus on some parameters like delta H value, and in certain cases we focus on the entropic factor also. So these kind of driving forces we will try to understand when we are talking about the molecular docking thing. So once you understand these driving forces properly, then what you can do? You can control that process properly. If you know all these factors, delta T, delta C, so you are able to control the process of your reactor design. So in the same way, you can consider this is something like a, you can consider there are some molecular reactors. So some kind of molecular engineering you are doing as you are knowing how to how these different parameters are coming into picture, which are related with this kind of hydrogen bonding electrostatic van der Waals interaction, which in short we can call as some kind of non-covalent interactions. What is the meaning of non-covalent interactions? Like which are not covalent. So you are not the actual perfectly bonded thing, but the non-covalent kind of energies. So if you know that, you can block the recognition. If you can control this thing, you can block some like in the example of HI1 protease molecule, I have told you that there are some these enzymes to which some inhibitor molecules can bind to it so that the virus won't remain infectious. So this kind of some blocking the thing you can do using some molecules, your pharmaceutical compounds, or you can even enhance the recognition. Maybe the pocket which is actually binding, you can attach some extra compound to it if you know the recognition, and the binding to some other component might be enhanced because you are able to play with the structure of the thing where it is actually binding. So you can actually block the recognition or you can increase the recognition. Okay. So now if you want to define this docking, what exactly I said, ultimately you are going to find out some kind of strength, some kind of binding strength will be there. So that we call it binding affinity, and delta G should eventually come into picture. So in this delta G value, we estimate something, delta G, we estimate some scores, and some kind of mathematical functions are useful to us where we actually do the scoring. So these are called as scoring function. So idea in the docking is, uh, you can read this definition also, but I have written this in more simple words. Like in molecular docking, what you actually do, you determine the interaction of two molecules and find the best orientation of ligand which would form a complex with overall minimum energy. Okay, I said it is simple, but just let's try to divide this in different parts. You first want to understand the interaction between two molecules in terms of some parameters. So I'm saying some delta G value you can use. And then how do you want to do this? You want to find out the best orientation of ligand with the receptor. You can consider like some like the ligand will be there which will tell like orientation means the same compound. Now I have to draw a three-dimensional object for that, but you can consider that same object in three-dimensional can bound from this side or some other side. So these are all the different orientation for the compound. So which particular orientation will be giving us the best fit with the receptor, that is important. So whatever will be the best fit, that you can consider the overall complex of the receptor and the ligand. The receptor ligand complex will be having the minimum energy. When the two things are binding with the highest affinity, they are going to have the minimum amount of energy. So this is what we want, and this is what will be the purpose of your molecular docking. Now, if you want to see, when I'm saying about that, you want to identify the minimum energy means what? So this example you can see here, like two things are there. One is the, you can consider to be a receptor, and another is a pharmaceutical compound. So now here in this example, the pharmaceutical compound has been shown in a very big structure, but you can consider like two things are binding to each other. When they are having, they are away from each other, you can consider both of them, their energy E1 and energy E2, they are at some high energy state. But when they are coming closer, so they are coming closer in such a way that the overall energy of the complex will be reducing. Okay, if I talk in terms of delta E, so energy of complex minus energy of 1 minus energy of 2, or this I can talk like energy of complex minus the summation of energy of both the components, like protein, it can be protein, and the ligand. So what should be the value of delta E if you have to do the docking? If you have to consider that water ligand it is going to bind, what should be the delta E value?
Negative.
It should be negative, like what we had earlier said, similar to your delta G value. Ultimately, this delta E value we can relate with the things like enthalpy, and we can see actually how two things can have a minimum amount of energy. So it should be negative. The overall energy should be minimized. So you can see there are different examples are given where two things can bind to each other at different places. Okay, in different ways, same two components can bind, and both the complex, even the complex formation, their energies won't be always the same for different kind of orientation of the ligand and the receptor. You can see this is all this. You can see the in the negative energies have been plotted the changes, and you can see which one is having the lowest energy, this particular one. So this is what you want to identify, like this particular compound, it is showing you the most negative binding at this place. So this is what you are going to measure, and you can say for this particular compound I have found out the binding affinity like this. So all these concepts are even same. Sometimes I said most of the time docking is you are using in the pharmaceutical drug design, but similar concepts sometimes people use also at the level of in the subject called nanotechnology. In nanotechnology also there are these kind of bindings when you have these structures like your graphene sheets or your carbon nanotubes or the fullerene kind of molecules. There also similar kind of concept people talk about when they want to capture something like in the here the receptor is your protein and something is binding to it. But imagine some kind of pure water purification you have to do and some impurity has to come and bind. So again there also the function delta G will be useful. Same thing with the carbon nanotube, something it can capture and it can bind permanently to it. So again the delta G value whatever it should come, that should be negative. So even at the level of material design, people actually sometimes use the molecular docking method, but most of the time their application are less. If you see the applications of molecular docking, like most of the time you can see the name. The docking is most commonly used in the field of drug design only, and you have always these uses like heat identification. I have already told you what is the identification of heat means, how to do the lead optimization, what is the best compound you have found out, how you can uh, tune the structure of that. So these are the major applications, but there are some non-medical applications also. Like if you want to predict some pollutants which are going to be bound to some enzymes and how the pollutants can be degraded by something. So in those kind of studies also, these molecular docking is useful. So even though these are not actually the drug design kind of study, but they are like somewhat related to your again the biological structure. Only for when you are going to utilize some actual nanomaterials like this graphene, carbon nanotubes or stuff, then you can say molecular docking you can use for some material design. Otherwise, most of the time it is related to the pharmaceutical drug design. Now, before we understand the last part of how to calculate all this binding affinity, there are these theories. These theories, three theories are there. One is called as lock and key theory. Another theory is induced theory, and the last theory is conformational ensemble theory. So all these three theory you can consider like they are from long time there, and before you do and find out your delta G, this theory should be understood well. So you can consider these kind of thing has been are there from long time. And the first theory, the lock and key theory, what does it talk about? It talk about some fundamental concept of docking. By the name lock and key, you can consider your receptor is always something like a lock kind of structure. And I said when the ligand bounds to it, it becomes active or deactive. So the ligand molecule, it is actually some kind of key which can only bind to it, and it can only create the therapeutic effect. It can only create that desired effect. If the two things are not able to fit properly, then the desired effect in most cases it won't come into picture. Okay, so this is the very basic theory that you can consider for docking. It is useful. But then when I say that the two things should fit with each other, so with what we are talking about, like you can see here, two puzzles kind of things are shown here. So where the one part is fitting within the other thing. So where like two perfect shapes you have found out in one something is missing and another something is present. So two things are binding to each other. So that we are going to consider as some kind of complementarity, some kind of similarity is there in terms of some shape. Okay, so two things are binding. But I said for that molecular recognition to happen, only the shape is not a single thing which is important, but along with that there should be some chemical complementarity. Some chemical complementarity means both the structure along with the shape, they should be also chemically they should be similar. So when I said chemically they should be similar, so there are this example, like as we are talked about the example of hydrogen bonding. So even like in the water molecules, hydrogen bonding takes place. There will be some hydrogen bond acceptor like oxygen molecules and the hydrogen bond donor. Hydrogen bond doesn't mean the something which is within the single molecule like the hydrogen is attached. It is between always, bet, not always between the two different molecules. There are examples like in protein itself, the hydrogen bonding can takes place within the same structure of two different parts of protein, but in most of the cases, like two different water molecules are there. So the hydrogen of this is going to interact with the oxygen of another water molecule. So this is something like a weaker bond. This is not a permanent bond like a covalent bond. This is a temporary bond which is created. So these kind of things are the driving forces for your molecular docking or binding of protein and receptor. So hydrogen bonding is one example, electrostatic interaction. There are some other example which are actually the type of van der Waal interaction. In some one of the classes, I will even talk in detail what exactly this interactions in like electrostatic very well, something between positive and negative or positive positive negative negative what happens. But some of you might not be having idea exactly what is van der Waal interaction. And there are some other types also like aromatic interaction. If two benzene rings there are coming closer, so pi interactions. Then there can be something like a hydrophobic interaction. So I can give you so many examples for this. We'll talk about these things in more detail. So all these things are but temporary thing, some kind of weaker binding, not I shouldn't say temporary thing. Some weak binding is there, not like your permanent covalent bond. So these kind of attachment should be there. Chemically, there should be some attachment. Then only you can say the two things, the ligand and receptor should bind. So whenever you are going to do the docking, this kind of if you try to calculate the values of this kind of interaction, so they should be always showing you some kind of negative changes, otherwise the feasibility won't be there. So this is the first theory which talks about that both the things should be having shape complementarity and the chemical complementarity. I'll just talk about this thing quickly and I will finish here. The second theory, it is the induced fit theory. What is the meaning of the word induced? Is something when two things are coming in contact with each other, it is not always necessary that both the things are going to fit perfectly. Like initially itself they are having the complementary shape. Okay, and even the interaction, it can happen that the two things are not having initially the complementary shape, but when they are going to come closer to each other, then they will undergo some conformational changes. Like I had shown you that video there, you have seen how the structure has changed its shape. So in the same way, you can consider some kind of alteration can happen within the molecule. It can happen in the your receptor structure, or it can also happen in the ligand structure also. So both of them are going to bind to each other, but they are not, they can, maybe they might not be able to bind sometimes initially. In certain cases they can bind, but in so many cases they are going to have some alteration in the state, so that they want to come up with a complex which will be having the lowest possible uh, energy. So this will be your final complex. So this induced fit theory talks about how the adaptation is going to happen when two things are going to come together. So this is also important. Okay, there is third theory. I will talk about that later and talk about some other concept later on. Okay. Any questions here?
Sir, I had a question regarding molecular orientation.
Mhm.
How do we control the orientation once the drug has been administered?
No, actually in your real